Hello, everybody. So now we are going to discuss the cases that we are going to cover in this chapter that we can solve analytically. And as I mentioned in the previous video, that the cases that we are going to deal with are very, very simple cases, which are mostly two-dimensional problems, and they're going to be very, very simplified so that these complex coupled partial differential equations can be solved analytically. So before we go through the problems that we are going to cover, it's better to have an idea of the approach or the procedure that we are going to follow in order to solve these kind of problems. And this is uh, and I think this is the logical approach that you need to follow. Whether you know the approach or not, this is how you should deal with these kind of problems. So, but it's good to have this approach in mind before we start dealing with the problem. So the first step is to set up the geometry. It's very, very helpful to have a sketch of the problem, and this is something we will have in all the problems that we are going to cover here, that we have drawing of the problem, so we know the dimensions, which is x, which y, which is z, and to have a feeling of the system. So this is a very, very important thing, because all the following steps will be built on our understanding of the problem, which will be very, very dependent on the shape of the system, which the sketch will help us understand. The next step is a very, 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 very important step, is to list all appropriate assumptions, approximations, simplifications, and boundary conditions. And these are all based on our understanding of the system. And this is why we need to read the problem statement very, very well. There are a lot of information that will be provided, and based on each one of these information, we can put an assumption or a simplification, or know some boundary conditions. And this is why this step is very, very, very important. And all the next steps are extremely dependent on step number two. Step number two is very, very critical, and this is when we go through the problems, you'd see that most of the time that we spend in the solving the problem will be in step number two, to make sure we understand the problem well, and we can translate all the information that we have in the problem into appropriate assumptions, so that the equations and the assumptions that we make translate what we have in reality properly, without having any deviations. And based on this, we can move to the next step, which is step number three, where we are going to simplify the differential equations, which are the equations of motion and the Navier-Stokes equation, based on the assumptions that we will make here. And then the rest is simple. We're going to integrate and then apply boundary conditions to get the constants of integration, and then we will get the results that we need, whether it's the pressure profile, the velocity profile, the shear stress, whatever the assumptions that or the requirements that we need to achieve, and finally to verify the results. So this is the procedure we're going to follow. Before going through some problems, I'd like to take some time to cover this step in some details, because the boundary conditions are important part of the solution. So we need to have an idea of the types of boundary conditions that we usually see or deal with. So there are some boundary conditions that are very common, and some of them are already known. So one of them is the no-slip boundary condition. So we have dealt with the no-slip boundary condition before in chapter 2, in the very, very beginning of the course, and we said that the no-slip boundary conditions means that the layer of the fluid in contact with a solid surface will not slip, meaning that it will have the same velocity as the surface. So if the surface is moving with a velocity u, then the velocity of the fluid is the same as the velocity of the wall. If the wall is stationary, then the wall velocity is zero, and so the velocity of the fluid is zero. So this is a very, very simple thing. And this is something we know from before. The second is what we call the interface boundary condition. It's very similar to the no-slip boundary condition, but with one important difference, is that the no-slip boundary condition is related to a fluid in contact with a solid surface. Here we have a fluid in contact with another fluid. So we have fluid A and fluid B. Both fluids are flowing in, let's say, the right direction as we see here. So the interface boundary condition focuses on the interface, this dotted line between these two fluids. So the interface boundary condition is very similar to the no-slip boundary condition. In the no-slip boundary condition, we said the velocities are going to be equal for the fluid and the wall. Here it's the same, that the two fluids flowing in contact with each other will have the same velocity at the interface. So the velocity of A is equal to the velocity of B at the interface. So this is the first thing we need to know about the interface boundary condition. Of course, if the two fluids are stationary, or there is no velocity at the interface, then the velocities will be equal to zero. But in general, the velocities at the interface are going to be equal for the two fluids. The second thing is that besides the velocity, the shear stresses are equal. So the shear stress of A at the interface is equal to the shear stress of B at the interface, which is a very useful relation. There is one special case which is a very useful case, or a case that we see a lot, is that we have what we call a free surface. We mean by a free surface, it's the surface of the fluid, let's say water or oil or anything, in contact with another fluid which is air. So if the other fluid is air, or in general any gas, but usually the gas that we deal with in our cases is air. So if this is air, then the shear stress due to the air is very, very, very small. Because the viscosity of air is very low, so the shear stress is very low. So if we have a free surface, then the velocities are going to be equal, and the shear stresses are equal, and both are equal to zero. So the shear stress of the liquid at the interface is going to be zero if the other fluid is gas or air. And of course, the pressure of the liquid is equal to the pressure of the gas. Okay, because we saw this many times before, that if we have a liquid that is in contact with the gas, then the pressure of the gas is the same as the pressure at the surface of the liquid. The third boundary condition is what we call the inlet or outlet boundary condition. It's something that is defined in the problem. For instance, you are told that the velocity at specific point is given with a specific value. You are given that, for instance, the pressure at specific point is given. So it's usually defined at the inlet or the outlet. So in these cases, we have the inlet or outlet boundary condition, which is defined based on the problem. So it's totally dependent on what is given in the problem, or what you know about the system that you deal with. The last one, which is a very, very common case that we see in many cases, like the pipe flow or similar things, which we call the symmetry boundary condition. The symmetry boundary condition is a condition that we can apply if we have an axis of symmetry. And of course, an axis of symmetry is a very well-known thing. So if an axis of symmetry is a line that splits the geometry into two identical parts or halves. So like for instance, the pipe flow, we have seen this many times before, that the profile on the top is equal to the profile at the bottom. So this is the center line is an axis of symmetry. And since it's axis of symmetry and both halves are identical, then what we have here at this point at the center, the velocities at the right side is equal to the velocity at the or the top and the bottom are equal, and so the slope here is zero. Or you can think of it as a maximum point or local maximum, so the derivative is equal to zero. So the change of velocity with y is zero. Okay, so this is due to the symmetry. There is one thing you need to know about the symmetry, which is an important thing, that the symmetry is valid when the geometry on the two sides is identical, meaning that if this is, let's say, 10 centimeter, then it's here 10 centimeter, so it's the same thing. And this is a very, very important thing. The second point is the conditions are similar on both sides. So here, for instance, we know that, let's say the velocity here is zero, then the velocity here must be zero. If for some reason we have here a velocity with a value different from the velocity in this value, we cannot apply the no-slip boundary condition. I mean the symmetry boundary condition. So the symmetry boundary condition is valid if the geometry is identical on the two sides of the axis of symmetry, and the conditions are also the same on the two sides of the axis of symmetry. So this is a very, very important point to keep in mind. There is one last thing I want to kind of remind you with before we go to the problems. And this is something I like to remind you with, because we will see it almost in all the problems that we are going to solve, which is about some of the conditions or the assumptions that we have to make. So there are some assumptions that are based on the Navier-Stokes equation. So we said before that Navier-Stokes equation is based on some assumptions, or is valid for some cases. It's valid for Newtonian fluids. So the fluid has to be Newtonian with constant viscosity or constant physical properties to be a general assumption. So it has to be constant physical properties and incompressible fluid and Newtonian fluid. So these three assumptions must be valid in any problem that we are going to solve using Navier-Stokes equation. This is very, very, very important. Okay, so this is something you can have as a built-in assumption in all the problems that we are going to solve, because if these three assumptions are not valid, we cannot use Navier-Stokes equation. Okay, so if we are going to use Navier-Stokes equation, then these conditions must be satisfied when we use this equation. The second is there are some assumptions that we will, as I told you, we have to deal with very simplified cases so that the problems can be solved. So the analytical solution is valid for only for these very limited cases. So there are some assumptions that I would say most of the cases, which is 99% of the cases, that these assumptions are valid. We deal with steady flow, and this is something you'd see in the problem statements, that you are dealing with steady flow. The second is we deal with laminar and parallel flow, meaning that the velocity, when we say laminar flow, laminar is understood, so there are no eddies, so the flow is in one direction. And parallel flow, meaning that there are no all the streamlines of the flow are parallel to each other. So it means that all the fluid has only one direction. Okay, the velocity has only one component. So if let's say it's a pipe and the fluid is flowing in this pipe, then the velocity has only one component. It's, let's say, Vx or Ux. So in this case, Uy and Uz is zero, meaning that the other two velocities are zeros. And these zeros are what simplifies the problem. So you need to know how can you make these terms zeros, and that you put the right terms equal to zero, not any term to be equal to zero. So this is the second thing. The last thing has to do with the two-dimensional flow. So we almost in all the cases that we deal with only two-dimensional flow. And this is You can know this by seeing this term. We are told in many problems that you have a plate that is infinitely long in, let's say, z dimension. So meaning that's infinitely long, that it's very, 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 very long, that this dimension is not affecting anymore. Okay, so the effect is due to the other two dimensions. So if let's say it's infinitely long in z, for instance, then the two parameters that affect the flow are x and y. So any change with z is equal to 0. This can be velocity with z, pressure with z, or whatever. So this slide is very important, and you need to keep it in mind when you solve the problems, because this is big part of the solution, if you remember, which is the assumptions and the boundary conditions. So this is how you can make some assumptions. So I'm going to stop here. Inshallah, when we deal with go through the problems, things will get more and more clear, inshallah. So next time we're going to solve one example, and then we will go through some more in the next videos. So see you then, inshallah. Goodbye.